As we get more comfortable with limits and we start evaluating different limits using numerical approach, graphical approach, or direct substitution, we run into a few issues, and we're going to try to tackle some of those today. So I put an example up here of a limit that I wanted to do, and I'm looking at the limit of this function as x approaches -3. The problem with direct substitution in this example is when I put a -3 in the bottom, I get a 0. And actually, when I put the -3 in the top, I also get a 0. So this unique thing is actually called the indeterminate form. It doesn't really have a definition. You can't take 0 things and divide them 0 ways. There's an issue there. There's a problem there. And it's actually a clue that I can do something to fix my issue of having that 0 on the bottom. So this example, I can actually divide things out. I have to do some factoring. But once I factor this, my x plus 3 that's on the top and the bottom actually cancel out. So the limit of this function is going to be the same as the limit of this more simplified function. Now when I go to plug a -3 in for x, I get -3 minus 2, which is -5, so I can actually evaluate the limit. Another thing that we come across is this idea of rationalizing. Now, we've dealt with square roots before when they've been on the bottom of a fraction, and we need to get them off of the bottom to the top, rationalizing the denominator. But in this example, we want to actually rationalize the numerator, because right now they want me to take a limit as x approaches 0, but x is on the bottom, and there's no factoring that I can do that's going to fix this issue. But if I take the top and I multiply by its conjugate, so square root of x plus 1 minus 1, its conjugate would be the square root of x plus 1 plus 1, and as long as I do the same thing to the top and the bottom, it's okay. I'm just multiplying by 1. But notice what happens on top. I FOILed this, and I got the square root of x plus 1 squared minus 1 squared. The squared and the square root are going to cancel, so I get x plus 1 minus 1. On the bottom, I didn't put these together. I left them separate, and you're going to see why. When I simplify my numerator, I get an x. To go with the x that's on the bottom, those cancel out, and I'm left with 1 over the square root of x plus 1 plus 1. Now when I go to do my limit, these two are essentially the same. When I plug that 0 in, I don't have that dividing by 0 issue anymore. So I plug a 0 in here, I get 1 over the square root of 0 plus 1 plus 1. Square root of 1 is 1, so 1 plus 1 is 2. I get 1/2. The limit of this function is 1/2, and I use rationalizing the numerator to help me with that. Sometimes we have to rely on doing this graphically as well. Here's an example where I'm taking the limit as x approaches 0, and there's my x on the bottom again. There's that problem, dividing by 0. But now I can't rationalize anything, I can't simplify anything, there's no way to fix that x. But if I take a look at the actual graph, as x approaches 0 from either side, the y is approaching 1. So this has an answer. If I take the time to look at the graph, it's 1. I had to just take the time to look at the graph instead of looking at it algebraically. Occasionally when we are evaluating limits, we run into one of our 3 situations where the limit does not exist. We have something that either oscillates, something that increases or decreases without bound, or something that approaches a different thing from the left and the right. I want to take a closer look at that situation, because we can also talk about one-sided limits. Limits that only work from either the left or the right. And all they do is they add this little symbol. This changes the limit. Instead of being a regular limit, it's only a limit from the left-hand side. This plus sign is only a limit from the right-hand side. So here's an example where this function does not have a regular limit. It's approaching different things from both the left and the right. But if we look at it in pieces, it's approaching positive 2 from the right. So if I look at a limit as x approaches 0 from the right side, it has an answer of 2. And if I look at the same function, but I look at the limit as x approaches 0 from the left-hand side, it's approaching negative 2. So these are considered one-sided limits because they only work from the left or the right. And the reason we talk about one-sided limits is the existence of a limit only occurs when we talk about these left and right-hand sides. So let me dive into that. It says if f is a function and c and l are real numbers, then this looks familiar to us. The limit as x approaches c of f of x is L, but the catch is if and only if both the left and the right limits exist and are both L. So this is how they define this limit, is they look at the left and the right and they say, okay, what's it approaching from the left? What's it approaching from the right? Is that the same thing? If it is, then we know that this has a limit by definition. If they're different, we can look at them as individual left and right one-sided limits. But if we want just a regular limit, we have to realize that the left and right have to be approaching the same thing. Last thing I want to take a dive into is this difference quotient. This kind of sets the stage for some of the things we're going to do in the next couple of sections related to tangent lines and slope and derivatives. But I'm going to do this difference quotient. It's a limit. We've seen these before in some of our pre-calculus work, but now we're diving into it with a purpose. So my original function is x squared minus 1, and this is the limit they want me to do. Now right away I see that there's an issue because I can't do direct substitution, so let's dive into this a little differently. Right here they're asking me to subtract f of 3, so I'm going to have to calculate that. And here they're wanting me to do f of x plus 3. So I'm going to take some time to do those two functions. F of 3 is as simple as plugging a 3 in here. So 3 squared is 9. 9 minus 1 is 8. So how I know that this is going to be an 8. F of x plus 3 takes a little more work because I have to take x plus 3, square it, and then subtract the 1. So I need to do some algebra here. I could FOIL, I could do box method, but I end up with x squared plus 6x plus 9, and then minus that 1. So I can combine those two things. I get x squared plus 6x plus 8. So now I'm going to take those two values and put them into this difference quotient. So f of x plus 3 minus f of 3, which is 8. Sorry, I'm using x's and h's. I'm getting this mixed up. This is supposed to be an h. So I'm going to apologize. I'm going to put my h in here. These are h's. Hopefully that doesn't throw you off too much. And I'm supposed to divide this by h. Notice that the 8 goes away, and what's left all have h's in them. So if I cancel out those h's, one of them here, one of them here, I get h plus 6. And if I go back to my original problem, the limit as h goes to 0, now I have all my algebra done. Now I can do direct substitution. Plug that 0 in there, 0 plus 6 is 6. So this difference quotient is something we're going to revisit as we dive deeper into limits and how they relate to slope, tangent lines, and derivatives.